Still, we are on the kernel of a linear transformation, and for these two given linear transformations, we are going to solve for the set of all vectors in R3 that will allow us to come up with a zero vector still in R3, because our transformation here is from R3 to R3. In short, we're going to look for the possible values of these components. Let's say that's vector v, okay? Components x, y, and z. We're going to look for the values, possible values of this, such that this would become a zero vector in R3. A zero vector in R3 is 0, 0, and 0. To do that, we simply need to copy this. We have x, y, and z is equal to this definition x, y plus 2z, and you have your z here. Again, we're going to look for the possible values of this, such as this equivalent x, y plus 2z, and then z is equal to the zero vector in R3, 0, 0, and 0. With that, we can now say x is 0, y plus 2z is 0, and z is also 0. And since this is the remaining equation, we simply need to use this z here. Y plus 2 times 0 be 0. Y is also equal to 0. Now that we have these three components for our set of vector v, that if all of these are 0, we will come up with a 0 vector here in our result. This would mean that our kernel will have, this vector of 0, 0, 0 will give us this 0 vector. In short, the kernel of T is a set containing that vector 0, 0, and 0. Okay, that's it. Next here is the same thing here. We are going to look for the possible values of x, y, and z in this transformation, such that its transformation x plus y, y plus z, and x minus z would be equal to the 0 vector in R3, which is 0, 0, and 0. Again, x plus y, y plus z, x minus z is equal to 0, 0, 0. We have x plus y be 0, y plus z be 0, and x minus z be 0. Since we have all of this in a form and we don't have a specific value for x, y, or z, let us use here matrix form. Unlike earlier where the values are exact, let's try to come up here with the matrix form and come up with a reduced or the row echelon form. For first, we have one let's use the augmented matrix 1, 1, 0, 0, because there's no z here, there's no x, 0, 1, 1, 0, and we don't have y here, 1, 0, and a negative 1, 0. Okay, let's make this 0. So we can here apply here negative 1 of our row 1 plus row 3 for a new row 3. Hence, we have 1, 0, 0, 0. We have here 0, 1, 1, 0. This becomes 0. Negative 1 times 0 is 0. Alright, sorry, negative 1 times 1 is negative 1, so we have negative 1 here. Negative 1 times 0 is negative 1 plus negative 1, negative 2, 0. Next, let's make this 0 by adding row 2 and row 3 for a new row 3. Okay? Oh, my bad. This is still 1. Right? Okay. Next, you will have here 1, 0, 1, 0, 0, 0, 1, 1, 0. Add this 2, we'll have 0. Add this 2, you have negative 1, and then 0 here. And finally, you see something like this here. Okay? We know that there's no exact value here. Okay, even if you're going to multiply this, of course, okay, let's try negative R3 for a new R3. You will have this final matrix 1, 1, 0, 0, 0, 1, 1, 0, 0, 0, 1, 0. But still, we have here this one here. This means that our z is equal to 0. Okay, that's our z now. Next, applying that in our second equation, which is y plus z equals 0, y is also 0. And for our first, we have x plus y be 0, x plus 0 is 0, so x is also 0. So we have these three components for our vector that can make a 0 vector. So this means our kernel of t is equal to the set containing this vector. So this is how we show the kernel of linear transformation here and here as well. It's just that we have separate steps here because we don't have exact value here. Anyway, we will have the same answers. So again, this is how we show the kernel of a linear transformation. Thank you very much for watching.